This story is not about the stars visible above the rooftop on a clear night. It is about what may be hidden between them, about forms of existence that perhaps surround us always, and that we have not yet learned to notice. We are accustomed to looking for life in our own image: water, oxygen, a warm planet resembling Earth. But if we look more broadly, the picture begins to blur, and the familiar words lose their precision. What follows will not fit into a single phrase. We will move from distant exoplanets, where spectral analysis today already discerns traces of organic chemistry in the atmosphere, to the subglacial oceans of Europa and Enceladus, where liquid water heated by gravity sloshes beneath a crust many kilometers thick. Then, to the methane seas of Titan, where water turns to stone and hydrocarbons serve as the solvent for a possible biochemistry. Then, to still bolder hypotheses: silicon organisms around scorching stars, plasma structures within coronae and accretion disks, beings for whom the open vacuum is a native environment. And further on, to a radical limit: life not bound to matter in the customary sense, distributed consciousness within fields of dark matter, informational structures upon multidimensional membranes, civilizations communicating not by radio waves, but through the resonance of space, which our instruments are incapable of registering. What is at stake here is not a plot, not a discovery to be announced at a press conference. What is at stake is a way of seeing, the familiar one in which we are the only known example, and another in which the silence of the cosmos means not emptiness, but only that we have not yet learned how to listen. And you, where do you draw the boundary for yourself? Between living and non-living, between what we are prepared to acknowledge as a form of existence and what we dismiss as coincidence. What matters more, to find life resembling our own, or to allow that it may look like something for which we have no words yet? Listen, this story is about that very boundary, and about how far it may actually run. The space around us is colossal in its scales, and at the same time remains almost entirely unexplored. The observable universe extends billions of light years in every direction, and within this volume there are billions of galaxies, each containing billions of stars, and with them, apparently, an untold number of planetary systems. When we contemplate these scales, one question arises on its own: how exceptional is our planet amid all this diversity? Earth possesses a combination of conditions that for a long time seemed unique: a stable orbit around a star of a suitable class, liquid water on the surface, a magnetic field shielding it from streams of charged particles, and an atmosphere with enough oxygen to sustain complex biochemical processes. It is precisely this combination that created the conditions under which life could not merely arise, but become complex to the degree we observe today. However, with the arrival of new observational instruments, the picture began to change, and it turned out that planets with similar conditions may occur far more often than had been supposed before. Among the exoplanets already discovered are those situated within the so-called habitable zone of their stars, at a distance where the surface temperature allows water to remain liquid. A characteristic example is a planet orbiting a red dwarf several tens of light years from us. Spectral analysis of its atmosphere indicates the presence of water vapor and of a number of chemical compounds characteristic of organic chemistry. This data does not provide direct evidence of life, but it does open the possibility of its existence, at the very least in the form of microorganisms, and in a broader hypothetical context of more complex biological systems as well. If life were confined only to planets resembling Earth, its prevalence in the universe might turn out to be low. But research of recent decades points to something quite different. Within our own solar system, objects have been found where conditions permit the existence of life, even if not in the form familiar to us. On the moons of Jupiter and Saturn, Europa, Enceladus, Titan, signs have been detected of subglacial oceans or of a dense atmosphere with chemical components capable of sustaining a biochemistry fundamentally different from Earth's. Beneath the many-kilometer icy crust of Europa and Enceladus, apparently oceans of liquid water are sloshing about, kept liquid by tidal heating, the gravitational influence of the giant planet upon the inner layers of the Moon. This heat can sustain geological activity similar to that which on Earth feeds the hydrothermal vents on the ocean floor. Such a scenario entirely changes our conception of what should count as a place fit for life. Life does not require sunlight, does not require an open atmosphere, a source of energy, a liquid medium, and a set of chemical elements are enough. This expands the horizon of the possible to a scale it is hard even to grasp mentally. If life is not tied to stellar illumination, it can be concealed beneath the surface of thousands and millions of objects across the galaxy. The scientific community is actively discussing a concept sometimes called the planetary paradox. Its essence is this: the conditions under which life is able to arise may be quite rare on cosmic scales, yet life itself, once it has arisen, demonstrates a striking resilience and an ability to adapt to the most varied environments. If life can build a functioning biochemistry on several different chemical foundations, then the number of biospheres in the universe turns out to be significantly higher than follows from the classical Earth-bound model, which rests exclusively on carbon and water. The panspermia hypothesis deserves separate attention, according to which organic molecules and, possibly, the simplest forms of life are capable of moving through the cosmos on board meteorites, comets, or as part of interstellar dust. If this hypothesis is correct, life on Earth may have arisen not on its own, but thanks to the transfer of matter from another part of the universe. And then we are merely one of the nodes in a significantly wider biological network. From the point of view of probability, this admits that life not only exists on isolated individual planets, but may be distributed across many stellar systems, joined by a shared history of the exchange of organic matter through interstellar space. Reflecting on the possible forms of extraterrestrial life, one cannot confine oneself only to the carbon-based biochemistry familiar to us from Earth's organisms. There are hypotheses that admit the existence of biological systems based on silicon, ammonia, or nitrogen compounds. Such systems would have a different chemical composition, would draw energy from different sources, and would, in all likelihood, perceive the surrounding world in a fundamentally different way. Signs of their activity may simply be invisible to the methods of detection at our disposal today. Reflection upon such forms of life inevitably compels us to reconsider the very definition of biology and raises the question of what intelligent life might, in general, look like under conditions radically different from those of Earth. And there is yet another level of hypothetical reasoning, the multiverse. If our cosmos is only one of a multitude of universes, each subject to its own set of physical laws, then the range of possible forms of life expands to limits that our imagination can hardly encompass. In another universe, where the constants of the strong interaction or of the electromagnetic force are somewhat different, entirely different atomic configurations may prove stable, which provides ground for biosystems based on a chemistry that simply does not exist in our cosmos. Theoretically, in such universes, the laws of physics may allow the existence of consciousness without a material carrier, or may sustain biological systems with a different structure of space and time. Modern methods of searching for life encompass several fundamentally different directions. The first is spectral analysis of the atmospheres of exoplanets, which allows one to determine their chemical composition remotely. The second is the study of extremophilic organisms on Earth as living analogs of possible extraterrestrial biosystems. The third is the search for radio signals bearing signs of an artificial origin. The fourth is the modeling of alternative biochemistries capable of functioning under conditions lethal to Earth's organisms. Each of these directions opens its own slice of possibilities, from the simplest microorganisms to highly organized civilizations that leave technological traces on the scale of stellar systems. Spectroscopy of exoplanet atmospheres is considered one of the most promising instruments of modern astrobiology. By analyzing the light of a star that has passed through the atmosphere of a planet transiting in front of it, scientists can reconstruct the chemical composition of that atmosphere with remarkable precision, detecting the presence of oxygen, methane, water vapor, carbon dioxide, and other compounds that on Earth are associated with biological activity. The detection of methane by itself is not yet proof of life, since this gas may have a volcanic origin. However, if methane is present simultaneously with oxygen in a ratio uncharacteristic of chemical stability without biological intervention, this becomes a weighty, indirect argument in favor of the existence of an active biosphere. Earth's extremophilic organisms open another path, not toward the stars, but into the depths of our own planet, to places where life long ago found ways to exist under conditions that once seemed absolutely incompatible with biology. The microorganisms inhabiting boiling acidic springs, the depths of rock under pressure exceeding 1,000 atmospheres, the Arctic ice at temperatures close to zero, all of them demonstrate that the biological machine is significantly more flexible than seemed the case half a century ago. Of particular interest are the organisms of hydrothermal vents on the ocean floor, which convert inorganic compounds of sulfur and iron into organic matter, needing neither sunlight nor oxygen for this. It is precisely such a scheme of nutrition that could function in the subsurface oceans of Europa or Enceladus, where the source of energy is the hydrothermal activity caused by tidal heating. The technological search for intelligent life is concentrated above all in the SETI project, the systematic listening to the radio range with the help of large radio telescopes. The logic of this approach is simple. A technologically advanced civilization is, with a high probability, using electromagnetic radiation for communication or as a byproduct of its activity, and part of these signals may propagate through interstellar space, ultimately reaching our receivers. A signal standing out against the background of natural cosmic noise by its regularity, its narrowband character, or its mathematical structure would be a direct indication of intelligent activity. It must nevertheless be borne in mind that the signals may have been sent thousands or millions of years ago. We are receiving only a temporal cross-section of the history of beings who, by the moment of our reception, may long since have ceased to exist. The James Webb Telescope has opened fundamentally new possibilities in the study of exoplanet atmospheres, working in the infrared range with unprecedented resolution. The infrared spectrum makes it possible to register thermal anomalies, regions of a planet emitting more heat than can be explained by geological processes alone. Such anomalies may indicate both biological activity, living organisms maintain an internal temperature, and the technological infrastructure of a civilization drawing heat away from industrial processes. Of course, the interpretation of such data demands great caution, but the very presence of an instrument capable of registering such signals at distances of dozens of light years represents a qualitative leap in observational capabilities. The detection of intelligent life, in addition to radio signals, may come through the identification of so-called megastructures, grandiose engineering constructions capable of influencing light, gravity, or the distribution of matter around a star. If a highly developed civilization is in need of enormous quantities of energy, one of the logical paths is to enclose a significant part of the surface of its star in a construction that intercepts the radiation. Such a structure would create characteristic periodic changes in the light curve of the star when observed from our side, differing from planetary eclipses by their irregularity or by their non-standard shape. Observation of several stars with unexplained variations in brightness is already regarded today as a potential clue in the search for artifacts of precisely this kind. On another scale, traces of technological activity may show themselves in the chemical composition of an exoplanet's atmosphere. Industrial activity, by analogy with what happened on Earth in the course of industrialization, with a high probability alters the ratios of gases in a planet's atmosphere, accumulating substances that cannot arise without a deliberate production process. To register such contamination remotely through spectroscopy is technically possible, and this makes even the negative consequences of a civilization's development a potential diagnostic instrument for an astronomer conducting observations from thousands of light years away. The existence of forms of life fundamentally different from Earth's biochemistry is also allowed by theoretical models of additional spatial dimensions. Contemporary physics, in attempting to unify quantum mechanics with general relativity, has arrived at mathematically grounded conclusions that the three spatial dimensions plus time familiar to us are only part of a more complex geometric picture. String theory, in particular, proposes that all observable particles in fundamental interactions are manifestations of the vibrations of one-dimensional objects vibrating in a space of 10 or 11 dimensions. There is as yet no direct experimental confirmation of this, but the mathematical apparatus is convincing enough for this idea to be taken seriously. If additional dimensions exist, they may influence the gravitational behavior of matter and the distribution of energy in a hidden way, too subtly for the instruments of today to register it unambiguously. But hypothetically, forms of life that take shape under conditions of a different number of dimensions would possess a fundamentally different physical nature. They could exist in states of matter inaccessible to our instruments, use physical principles that seem impossible to us, and interact with our universe only indirectly, through gravity, electromagnetic effects, or quantum correlations. In such a context, life may manifest as a distributed energetic field, as a collective informational structure, or as something for which we have not yet formed either a concept or a description. The hypothesis of parallel universes suggests that our universe is only one out of an uncountable number, each of which is subject to its own physical laws. In one of these universes, atoms with different combinations of protons and neutrons may prove stable, which opens the possibility of organic systems on an entirely different chemical foundation. Under such conditions, consciousness, theoretically, may develop as a quantum or energetic phenomenon, needing neither protein molecules nor cellular membranes, nor, in general, any discrete material structure at all. Dark matter and dark energy, which make up the overwhelming part of the mass energy of our universe, remain to this day a mystery. We observe their influence on the motion of galaxies and on the large-scale structure of the cosmos, but we can neither register them directly nor understand their nature. One hypothesis holds that dark matter is a form of substance from additional spatial dimensions, interacting with our world only through gravity. If this is so, then within dark matter, theoretically, structures of its own may exist, regularities of its own, and possibly forms of activity we would be compelled to call life, without having the slightest way to detect it by the familiar means. Returning to the three familiar dimensions, let us examine conditions that seem incompatible with life at first glance, but turn out to be potentially fit for it upon more careful study. Earth's extremophiles have already shown us that biochemistry is far more flexible than had been supposed, and this flexibility permits the building of ever bolder hypotheses about life in the most unexpected corners of the cosmos. In the depths of Earth's crust, microorganisms have been found at a pressure exceeding 1,000 atmospheres, in the complete absence of sunlight and under conditions in which most known organic molecules would long ago have broken down. A special place in this series is occupied by Titan, the largest moon of Saturn, whose surface is covered with lakes and seas of liquid methane and ethane. The temperatures there are so low that water freezes, becoming a solid mineral, a geological rock, not the substance familiar to us. Yet it is precisely under these conditions that biochemical processes may be possible. based on liquid hydrocarbons as a solvent replacing water, and on the synthesis of organic molecules from nitrogen-bearing compounds. Hypothetical organisms inhabiting the methane lakes of Titan would draw energy from mechanisms fundamentally unknown to Earth's biology, and would function at temperatures at which the biochemical reactions of Earth cease entirely. In the atmospheres of gas giants, Jupiter, Saturn, Uranus, and exoplanets similar to them, there exist complex organic compounds, powerful electrical discharges, and dynamic convective flows. Under certain conditions, the particles and molecules suspended in the atmosphere can form stable structures sustained by the continuous motion of the gaseous layers. Hypothetically, under such conditions, there could exist organisms in the form of gaseous or plasma structures, maintaining their energy balance through chemosynthesis or electrical discharges, and moving together with the atmospheric currents, adapting to the shifts in pressure and temperature. Silicon life is yet another hypothetical variant that attracts the attention of researchers. Silicon, like carbon, is capable of forming long molecular chains, although with a lesser variety of configurations. At high temperatures destructive to carbon structures, silicon may form stable compounds that permit biochemical reactions to proceed. Planets with a scorching surface, on which Earth-based biology would not last a second, could theoretically be home to organisms using silicate structures as the basis of cell membranes and building their metabolism on a chemistry in which a temperature of several hundred degrees is the norm rather than a catastrophe. Radiation is yet another condition that Earth's life has to a certain degree learned to overcome. Some microorganisms are able to withstand powerful radioactive exposure, restoring damage to DNA with astonishing efficiency. If we develop this logic further, hypothetical organisms that evolved in regions of space with intense radiation, near pulsars or within the radiation belts of planets, could not merely tolerate exposure, but actually use it as their principal source of energy. Their biochemistry would be built upon structures resistant to ionization, and their mechanism for extracting energy from the radiation flux would become the analog of photosynthesis, only applied to gamma radiation or to streams of charged particles. The idea of life in vacuum sounds even more radical. Yet even here there are Earth-based precedents. Some microorganisms preserve their viability after a prolonged stay under conditions of nearly complete absence of pressure. If we imagine that such resilience turned out to be an initial condition rather than an incidental acquisition, then evolution could have built organisms for which open space is their native habitat. Such creatures would draw matter from cosmic dust using electrostatic charges or weak gravitational fields to maintain their own structure, and would exist within a range of nanoscales, which would make their detection with the aid of modern instruments a task all but insoluble. The cryogenic conditions of deep space, where the temperature approaches absolute zero, open up yet another hypothetical corridor. Biochemical processes at such temperatures slow down to the extreme, but may remain stable over colossal stretches of time. Organisms existing at the threshold of absolute zero could theoretically employ quantum tunneling processes for the transfer of energy and information, a mechanism that has no analogs in warm biochemistry. Their biosystems would function on principles closer to quantum physics than to traditional molecular biology, and would constitute something fundamentally other than what we are accustomed to calling life. Plasma life occupies a special place in the spectrum of exotic hypotheses. Plasma is a state of matter in which atoms are deprived of their electrons, which creates an environment of high conductivity and of activity of charged particles. Under conditions of extremely high temperatures, in solar coronae, lightning discharges, accretion disks around black holes, plasma structures can form stable configurations sustained by magnetic fields and by the dynamics of charge flows. If such structures are able to close loops of exchange of energy and information according to a principle analogous to biological metabolism, we have every ground to regard them as a hypothetical form of life, existing on entirely different temporal scales and fundamentally imperceptible to instruments tuned to chemical detection. In the darkest and most rarefied regions between galaxies, where the density of matter is minimal, the existence of hypothetical life based on informational or field-based structures is also admitted. These biosystems would function at the level of fundamental interactions, using weak quantum fluctuations of the vacuum as their source of energy, and their resilience would be determined not by chemical bonds, but by interactions of fields. To any outside observer confined to the familiar physics, such structures would be invisible, something scattered through the void, yet at the same time structured, informationally active, though in a way entirely other than a protein cell. If space really is multi-layered, and theoretical physics offers arguments weighty enough in favor of this, then life taking shape under different geometric conditions moves beyond the bounds of any biological templates constructed on the basis of earthly experience. Classical physics describes our world through 3 spatial dimensions and 1 temporal, forming a 4-dimensional structure. Attempts to unify quantum mechanics with general relativity, however, again and again lead to models in which this scheme is only an approximation of a more complex reality. According to a number of theoretical models, additional dimensions may be compactly folded up into structures of an extremely small radius, inaccessible to direct observation. Their existence can be detected only indirectly, through their influence on the gravitational behavior of matter at the corresponding scales, or through anomalies in the distribution of energy across the cosmos. If these dimensions are real, then the familiar notions of cell membranes, molecular mechanisms, and energetic exchange become too narrow a frame for describing the whole possible spectrum of biological systems. In a multidimensional environment, an organism is not required to have a surface in the familiar sense. What in 3-dimensional perception looks like a stable form may turn out to be only a cross-section of a more complex object existing simultaneously along several coordinate directions. Contact with such a form of life would be perceived as interaction with an unstable structure changing its configuration, whereas in its own frame of reference, this structure would be entirely constant and well-defined. Theories of additional dimensions also open up a new view of energy mechanisms. If the topology of space is more complex than we are accustomed to assume, then the transfer of energy may occur along trajectories that in a 3-dimensional world seem inexplicable, vanishing at one point and appearing at another with no visible connection between them. It is precisely by such models that the behavior of dark matter, in particular, is explained. Energy does not disappear, but is redistributed through additional coordinates inaccessible to our detectors. This opens the possibility of the existence of beings using other channels of energy exchange, and then their activity would show itself in our world only as weak fluctuations of gravitational fields or as non-standard electromagnetic disturbances. Some physical models admit the existence of what are called multidimensional membranes, structural surfaces separating different layers of space. Life taking shape upon such membranes would possess entirely different constraints. Its development would depend not on chemical reactions, but on the stability of the geometry of the surface itself, its curvature, the density of energy, the amplitude of oscillations. In 3-dimensional perception, such forms of life would look like dynamic structures, continuously changing their configuration under the influence of external factors. There are theories that allow that multidimensional entities are capable of moving between the layers of space without destroying their own structure. For such beings, the familiar barriers, distance, the density of the medium, temperature, would have no defining significance. In a 3-dimensional model, their movements would be perceived as the sudden appearance or disappearance of objects with no visible cause. Some unusual astronomical phenomena have been proposed for explanation precisely as the crossing of spatial layers. Although such interpretations remain strictly hypothetical, the idea of a multi-layered structure of space itself does not leave the agenda of theoretical physics. If we regard multidimensionality as a real property of the universe, then the temporal structure too becomes more flexible. In several theoretical models, time is regarded not as a single linear axis, but as a property depending on the geometry of space. And then in different regions of a multidimensional universe, time may flow at different relative rates. Life from such regions would perceive the processes of our three-dimensional world as slowed down or sped up, which creates additional difficulties for any conceivable interaction. Any attempt at contact with entities living within a different temporal regime would lead to a mismatch of the perceived informational flows. Both sides could transmit signals, but each would perceive them as chaotic noise devoid of internal structure. Modern astronomical observations, the detection of gravitational waves, the study of the distribution of dark matter, the monitoring of high-energy cosmic rays, are gradually refining the models of a multidimensional universe. In several studies, an unusual distribution of energy in cosmic rays has been considered, which theoretically may arise from the transitions of energy through additional spatial directions. Such interpretations remain hypothetical, but they demonstrate that multidimensional models are applied not only in abstract mathematical reasoning, but also in the analysis of real observational data. Gravitational waves, interacting directly with the geometry of space, are regarded as one of the potential instruments for detecting multidimensional activity. If additional dimensions exist, they may influence the character of the propagation of gravitational waves, creating faint but fundamentally inexplicable deviations within the framework of the standard model in the shape of registered signals. Methods of data processing continue to be refined, and what today is lost in the noise may tomorrow turn out to be precisely the anomaly we have been searching for so long. Since the moment when the idea of the possible existence of other civilizations became a serious scientific subject, researchers have sought to understand in what manner technologically advanced intelligent beings might leave traces distinguishable to us from afar. These traces have come to be called technosignatures. They may take the most varied forms, from structured radio pulses to megastructures capable of altering the flow of light from a star, redistributing gravity, or concentrating matter into configurations impossible without a directed engineering effort. Radio signals remain, as before, one of the most logical candidates. Radio waves are relatively easy to generate, direct, and receive across interstellar distances. This makes them an obvious tool of communication for any civilization that has mastered electrodynamics. A signal standing out against the background of natural astrophysical noise through its regularity, its narrowband character, or its repeatability, one that cannot be explained by pulsars, quasars, or other known sources, would be a weighty indication of intelligent activity. It must at the same time be borne in mind that there are limitations. The signal may not be directed toward Earth. It may prove too weak by the moment of arrival, and the civilization itself may have vanished thousands or millions of years ago, long before we switched on our receivers. The radio range, however, is not the only channel by which information can be transmitted across interstellar space. There exists a fundamentally different approach: directed laser and optical signals which, unlike radio waves that scatter, can be concentrated into an extremely narrow beam of light and preserve this directionality across enormous distances. A technologically advanced civilization that understands the physics of electromagnetic radiation would almost inevitably regard the optical range as one of the most effective instruments of communication. A sign of such a signal might be the briefest but extremely bright blink at a strictly defined wavelength, a flash strikingly unlike any random natural phenomena in its structure. Present-day ground-based and orbiting observatories are already conducting a search for such optical pulses, proceeding from the assumption that intelligent beings are able to use them as an interstellar beacon visible thousands of light years from the source. Amid the stellar background, such signals may be concealed, but highly sensitive equipment allows them to be picked out by characteristics that in principle are not reproduced by natural processes. Another category of technosignatures is connected not with communication, but with construction. A civilization that has attained a sufficiently high technological level sooner or later encounters the limitedness of the energy resources of its own planet. And a logical response to this challenge becomes to turn to its star as an all but inexhaustible source. If one were to build a construction around a star that intercepts a significant part of its radiation, such a structure would inevitably show itself in the light curve of the star when observed from a sufficient distance. Light would be either blocked or redirected, creating irregular, non-standard shaped changes in brightness, resembling neither the transits of planets nor pulsations. The concept of such a construction, known in the scientific literature as a Dyson sphere, has long become part of a serious astrophysical search, and several stars with unexplained fluctuations in brightness are already under close observation, although no single case has as yet received an unambiguous explanation in favor of intelligent intervention. If a megastructure exists and absorbs significant flows of energy, part of this energy inevitably passes into heat and must be dissipated. Otherwise, the construction would simply be destroyed. As a consequence of this, there is an excess of infrared radiation, which cannot be explained either by the geological activity of planets or by other known astrophysical processes. Space telescopes working in the infrared range are capable of detecting such thermal anomalies through targeted scanning of galactic structures. A hotspot where there ought not to be one is a potential trace of an infrastructure working with colossal energetic flows. Apart from megastructures, indirect evidence of technological activity may be provided by artificial objects in orbit, satellites, stations, fragments of engineering systems that a civilization has left around its home planet or neighboring bodies. Even if the beings do not intend to be detected, their orbital infrastructure reflects light and can be registered as an object with unusual geometric characteristics or non-standard behavior. Too stable, too symmetrical, too resilient in orbital mechanics to be explained by natural origin. Signatures that lie outside the traditional electromagnetic range deserve separate consideration. Ultraviolet, X-ray, and gamma radiation, streams of neutrinos, or modulations of gravitational waves. All of this may theoretically serve as a channel for the transmission of information for a civilization possessing technologies fundamentally superior to our own. Neutrino streams are especially interesting in that a neutrino practically does not interact with matter and is able to pass through a galaxy without weakening, an ideal carrier for a directed signal if the sender has the corresponding generator and the receiver a detector of sufficient sensitivity. Present-day neutrino observatories register particles of high energies, but a systematic search for structured patterns in neutrino streams remains a task for the next generation of instruments. Mathematical structures within a received signal may prove to be the most convincing marker of an intelligent origin. Sequences encoding prime numbers, or the Fibonacci series embedded into the rhythm of pulses. Such patterns do not arise in pulsars, in quasars, or in other known astrophysical sources. Information encoded in this way would be at once a signal and a test. Only a civilization that has attained a certain level of mathematical understanding is capable of recognizing and deciphering such a structure. This creates a kind of filter, deliberate or not, where the very act of recognition is a condition of dialogue. Finally, traces of technological activity may be detected not in signals and not in structures, but in the composition of an atmosphere. Industrial activity analogous to Earth's industrialization inevitably alters the chemical balance of a planet's envelope. Compounds accumulate that do not occur without deliberate production. Fluorine-bearing gases, chlorinated molecules, unstable isomers uncharacteristic of natural geochemical cycles. Spectral analysis of the atmosphere of an exoplanet that reveals the sustained presence of such anomalies turns pollution into a diagnostic instrument. A civilization may not wish to be detected, but the chemical traces of its activity it inevitably leaves behind. The very interaction between civilizations can take fundamentally different forms. Active contact assumes that one of the sides is sending a signal, expecting a reply, and thereby taking upon itself the risk of being detected. Passive observation is an entirely different strategy. A civilization studies, records, analyzes, but does not intervene, preferring to remain in the shadows. Hypothetically, a situation is also possible in which signals are deliberately constructed so as to look like natural phenomena to observers not sufficiently developed, and to open themselves as a message only to those who have attained the necessary level of understanding. It is precisely for this reason that the search for technosignatures requires not only technical means, but also a continuous revision of the very models of the behavior of intelligent beings. We are not merely searching for signals. We are constructing hypotheses about how those we have never yet seen might think. But even the most large-scale efforts of the search have not, to this day, given an indisputable result, and this fact has several deep explanations. The first of the barriers is temporal. Civilizations arise, develop, and vanish on scales incomparably surpassing human history, and the window of their technological activity, the period during which they are capable of transmitting detectable signals, may be vanishingly short by cosmic standards of time. If this window has not coincided with ours, the signal simply no longer exists. It was sent, passed through interstellar space, and dissipated long before our civilization attained the ability to receive it. The second barrier is physical. Interstellar distances weaken, scatter, and distort any signal with an inevitability that cannot be overcome without a colossal power of the transmitter or without very precise aiming in a particular direction. The communication technologies at our disposal may quite well prove incompatible with the methods used by a civilization of another level of development. Our receivers are tuned to those ranges that seem logical to us ourselves, not to those we are searching for. The third barrier is the most difficult to overcome, precisely because it is internal. Human perception is arranged such that we tend to project onto hypothetical civilizations Earth's communication models, Earth's technologies, and Earth's intuitions about what a rational signal ought to look like. If an extraterrestrial mind expresses itself in a way for which we have no categories, we shall see in this only noise, a natural anomaly, or a coincidence, and pass by without even realizing what has happened. The silence of the cosmos does not prove solitude. It may only indicate that we have not yet learned to listen within the necessary range. Meanwhile, the very question of how life arises and develops under conditions different from Earth's is becoming ever more central for astrobiology. The key idea here is that evolution as a principle, and not as a concrete biochemical mechanism, is able to be realized within the most varied environments. For it to be set in motion, three conditions are enough: a source of energy, structured matter, and the possibility to accumulate changes between generations, or their analogs. The carriers of hereditary information in such systems need not be nucleic acids. The same function may hypothetically be performed by crystalline matrices stable at extreme temperatures, or by polymer chains functioning in an environment of liquid ammonia, provided that they are capable of self-copying with variability subject to selection. The question of alternative solvents plays a special role here. Earth's life is built around water, a liquid unique in its physical and chemical properties. Ammonia has a significantly lower freezing point and a different ability to dissolve organic compounds, which makes it hypothetically a suitable solvent for a biochemistry within worlds of low temperatures. Metabolic cycles within ammonia oceans would probably proceed significantly more slowly than those on Earth, but it is precisely such slowness that could provide the resilience of structures in the long-term preservation of energy. Under such conditions, selection would apparently favor organisms with the most economical exchange of substances and the greatest structural stability. The hydrothermal vents beneath the icy crust of Europa and Enceladus remain one of the most concrete places where such evolution could be occurring right now, within our own solar system. Where gravitational heating sustains geological activity, there arise local zones of warmth and of chemical gradients suitable for the concentration of organic molecules and for their subsequent self-organization. It is precisely around the mineral surfaces of hydrothermal vents, capable of catalytically accelerating reactions, that the first self-sustaining structures could form, the precursors of what we call the living. On Earth, the path from the simplest molecular assemblies to the first multicellular organisms took billions of years, and there is no reason to think that somewhere this path would have been fundamentally shorter. Although in the conditions of a more active, energetic environment, it might have proceeded faster. Among the exotic directions of evolution, particular attention is deserved by systems adapted to a high radiation background. On Earth, ionizing radiation is a destructive factor, yet certain microorganisms already demonstrate a striking ability to restore damaged molecules with exceptional efficiency. If we continue this logic, we can imagine organisms for which radiation has ceased to be a threat and has become a source of energy, a peculiar analog of photosynthesis, but applied to streams of charged particles, or gamma quanta. Such structures would develop in the direction of an increase in resilience to ionization and of a refinement of the mechanisms of restoration, and their biochemistry would be fundamentally unlike that of Earth. Under conditions of high gravity, evolution would apparently push forms of life toward compactness and density, toward structures capable of withstanding enormous loads without destruction. Conversely, where gravity is weakened, selection could create large and light configurations, using the slightest gradients of pressure or of temperature as the driving force. In the atmospheres of gas giants, where there is no solid surface and no clear boundary between zones of different composition, evolution could form floating colonial structures, holding energy in the form of electrical charges and exchanging matter through gaseous flows. The transmission of hereditary information in such systems could be recorded not in molecular sequences, but in the distribution of energetic states, a physical rather than a chemical memory about stable configurations. If evolution reaches a point at which biology becomes not an obligatory condition, but only one of the possible carriers, a fundamentally different space for reflection is opened up. Consciousness, in its most general understanding, is the ability of a system to process information, adapt to changes of the environment, form stable patterns of interaction, and preserve identity through time. The brain is one of the realizations of this ability, but not the only possible one. In zones of strong gravitational gradients, near supermassive objects, in regions where the geometry of space is deformed under the action of extreme masses, pseudo-stable configurations may theoretically arise, whose dynamics is determined not by chemical reactions, but by the interaction of energetic nodes. Such nodes would perform functions analogous to neural connections, but based upon an entirely different principle, for example, upon the resonant maintenance of frequency patterns. Models of distributed consciousness consider scenarios in which personality is not concentrated in a single point, but fragmented among several structures, preserving integrity through the synchronization of processes. Under conditions of a multi-layered space, each layer sustains a certain type of interaction, and consciousness as an assemblage of processes could exist in a distributed manner, without a fixed location, without biological cycles, without a body in the familiar sense. The stability of such a system would be determined not by the durability of its individual components, but by the ability of the whole network to sustain the coherence of the patterns. As long as the resonant frequencies of the internal processes coincide with the oscillations of the environment, the system preserves itself. Communication between such forms of consciousness would take place not through traditional signals, but through a change in energetic configurations perceived as structures of meaning. Contact between different layers of reality would become possible upon temporal synchronization. At that rare moment when the parameters of the energetic oscillations of two different systems prove sufficiently close to form a zone of intersection. Such a zone could exist only for a limited time, yet for a distributed consciousness not bound to biological limitations, this may be enough. Such consciousnesses would probably perceive time not as a linear flow, but as an assemblage of states accessible under certain conditions of synchronization. Change for them would mean not movement from one moment into another, but a change in the configuration of the environment in which they exist. The internal dynamics of cosmic ecosystems built upon such principles differs fundamentally from anything we observe on Earth. Stability here is determined not by physical reproduction and not by chemical cycles, but by the coherence of patterns of oscillations between different layers of the medium. The components of such ecosystems are not required to have a material envelope. Their integrity is ensured by a correlation between local and global processes. Gravitational and electromagnetic fields play the role of the principal carrier of information, and the exchange of signals takes place not through material objects, but through the modulation of energetic flows. This creates the possibility of the formation of networks of interconnected structures, resilient to external disturbances, precisely because their connections are non-material and cannot be severed by mechanical action. Four key mechanisms define the evolution of such systems. The first is the ability to store and process information within non-traditional carriers, distributed energy fields, plasma structures, or multidimensional configurations of space, which preserve the identity of the system even under significant changes of external conditions. The second is adaptation to the variable energetic and geometric parameters of the cosmic environment. The use of gradients of temperature, of density of matter, or of electromagnetic fields to sustain stable patterns during slow but stable development. The third is interaction through hidden or multidimensional layers of the medium. If space has additional dimensions, information propagates through them, uniting distant regions into a single functional network, unrestricted by the speed of light in three-dimensional space. The fourth is the ability of self-replication through the modification of patterns. The system alters internal configurations, tests their resilience under changing conditions of the environment, and reproduces the most viable variants, an informational selection in place of a biological one. Hypothetical interstellar civilizations possessing such mechanisms could exist for billions of years, gradually uniting distributed patterns into unified functional structures, collective consciousnesses, in which individual components lose their autonomy and the system functions as a single whole of exceptionally high resilience to any disturbance. Interstellar communication for them would be carried out not through radio signals and not through laser beacons, but through the synchronization of energetic and informational structures across distances measured in light years, through quantum correlations, or through changes in the structure of space perceived as patterns of meaning rather than as physical signals in the familiar sense. For human technology, such interactions remain invisible, not because they do not exist, but because our instruments are tuned to a different level of reality. We know how to register electromagnetic waves, gravitational disturbances, streams of particles, but we do not yet know even how to formulate what precisely an interaction with an informational system existing beyond biology and beyond three-dimensional geometry would look like. The evolutionary prospects of such forms include an endless complexification through the optimization of the processing of information, an expansion of the range of interactions, and the formation of ever more large-scale networks of collective consciousness. Structures capable of embracing whole stellar clusters without needing physical carriers and leaving no traces accessible to our present methods of detection. All this allows us to look at the cosmos differently, not as a physical medium we study from outside, but as a space within which an untold number of forms of interaction is taking place, most of which remain, for now, inaccessible to us. Life in the universe may manifest in forms decentralized, multidimensional, and informational energetic in their nature, and our search will become truly complete only when we learn to ask not merely the question, is there life out there? But a much more difficult question. In what sense of the word life are we conducting this search at all? Write please in the comments how you like this story. It matters to me to understand whether it caught you. What do you think? The thought that life in the universe may exist in forms we are fundamentally incapable of detecting with our instruments. Does it rather calm you or unsettle you? And tell me also, is it more comfortable for you to watch horizontal video or vertical for the phone?